Looks good. Remember there was, oh, I'll talk about that later. So this is, let's go over the quiz, okay? I haven't really looked at the scores of the quiz, but I'm going to go over the answers. And that is down here at the end of set theory. And I'll do a preview. So this way I don't get to see the actual answer. I have to do the answer myself. All right, so the first one is A is a set with two elements AB, B is a set of three elements A, B, and C. Which of the following is true? A is a subset of B, looks about right, but I would evaluate all of them, okay? Because just in case I misunderstood the concept and something else seems to be true as well, then I have to evaluate both of them and go like, okay, which one is actually true? A is an element of B. No, that's not true, okay? That is not the case here. B is a subset of A. That is not true because B has more elements than A, so B cannot possibly be a subset of A. B is an element of A. Once again, it cannot be true. So one is actually A is the answer. Okay, moving on. Second question. So the second question is something I have to grade manually. The question gives you the constraints. A union with B has 5 elements, A, B, C, D, E. So that means these elements, A, B, C, D, E, can be found in at least one of the two sets. Okay? A minus B, which means those are the elements exclusively in A but not in B, are C and E. Define a membership arrangement. In other words, tell me how you can put elements in A and B so that they satisfy the constraints already stated. Okay. Enter or type your answer in the HTML editor area. Be sure to use all the correct notations. So let's go ahead and do it here. There's no need to use the equation editor if you do not feel like it, and that's partially why I chose to use all just very simple elements. Okay, so what has to be in A? C and E has to be in A, right? Those two must be in A because they're in A minus B, right? Okay. We also know that the union of A and B has the other elements, which are A, B, and D. Okay. So we'll go ahead and do it like this: A, B, and D. So I'm going to stop and I would reevaluate. If A is just CE, only has CE as elements, if B only has A, B, and D as elements, does it meet the requirement? Does it meet the constraint? The union would consist of elements from both, so that would make up A, B, C, D, and E. So it will satisfy the constraint that is set up by the union, but does it satisfy the requirement of A minus B? In other words, if I look at the elements that are only in A but not in B, are those consisting only of element C and element E? That is true as well. So this will fulfill that requirement. What else is going to fulfill that requirement? Yep, we can throw more stuff in A. That's fine. Okay. So does that answer the question? Are there any points or questions about the answer of this particular question? Uh-huh. You get C and E because A minus B would consist of the elements. It would be a set, okay? And that particular set consists of only elements that you can find in A but not in B. The elements that are in A but not in B are C and E only. Yep.
But there are like sub possibilities for A. Like you can have ACE or BCE or DCE, or you can have like D.
Yes, you can have some additional ones. Okay, so you can have ACE, you can have BCE, DCE, and then you can have ABCE, ADCE, and ABC, ABDCE. So all of those can work correctly as well. So this is the smallest you can get A to become. But A can contain additional elements from B. It will still fulfill those requirements. So maybe a better question is how many ways can we arrange A to satisfy that requirement? Hint, hint, exam one. Yep. Sorry? Sorry? 8 different ways. So ABC, ABD, and then the two, 1, 2, 3, 1, 2, 3. Right. Okay. Yep. Exactly. So there are 8 ways to do it. Because, okay, that's because each element of B, A, B, and D can either be present or absent in A as well. So we have A either present or absent, B being absent or present, D being absent or present. So that's 2 times 2 times 2, and that's why there are 8. So there are 2 ways to get to the 8, number. One is to enumerate, and say, okay, none of those, all of those, any 2 of those, you know, or you can look at it from the perspective of a Boolean of whether A is in there or not, B is in there or not, or C is in there or not. So very good. That's good analysis. Okay, so let's move on. Okay, so this one was brought up a little bit earlier on Monday. The answer is false. The answer is false. A by itself is not an element in a set that consists of a set of an element of A. It's kind of asking, if A was a file, okay, and the other side is a folder that contains a file called A. So the question is this file in that folder, but not in a recursive sense? Okay, because we are not asking about recursive containment. We're only asking at the top level of this set, is A an element? And the answer is no, A is not an element of that particular set. Is that okay or not? Okay. So the answer is false on this one. And then question number 4. Choose the correct answer. ABC is a subset of ABC, and that is true. Okay, it would be false if I have changed the symbol. Instead of using subset of, if I change it to the proper subset of, which means it doesn't have that under bar, then the answer would be false. Okay. Moving on. Choose the correct answer. ABC as a set union with AB is the set of ABC, and that is correct. Number 6. Number 6 is a good one because it asks the question of, regardless of how we define A and B as sets, is the following always true? That's what it's asking. Okay. So we have to look at A minus B equals to an empty set, which means there are no elements that are distinct in A but not in B. Okay. Does it imply that A is not a proper subset of B? Okay, so let's analyze it a little bit more. What makes A a subset of B? There are things in B that are not in A, right? But because of the negation says A is not a proper subset of B. Okay? If A is not a proper subset of B, that means the negation of what I said a little bit earlier would be true. In other words, it is not the case that there are elements in B but not in A. Okay? So if A minus B is an empty set, it means everything in A is also in B. Okay? If that is true, then A is a subset of B. May not be a proper subset, but it has to be a subset of B. So what do you think of this implication? If this one is true, can you construct a case that this one is false? The answer is yes, so that means it is false. The implication itself, it is not always true. Okay, let's use an example. Okay, let's write and use an example. I got the tablet to work by changing some of the settings of the browser, interestingly. So I can actually use it now to capture my notes. I don't have to use the whiteboard anymore. Okay. It took me a while to figure out what's wrong with the settings in the browser. So as it turns out, I have to enable some of the experimental features in Chrome to get this extension to work. So let me fire that up here. Okay. So it has a significant lag, so I'm still trying to figure out how to reduce the lag, but at least it's working. All right. So we want to make a minus b equals to an empty set true. Okay. So everything in A has to be in B as well. Okay, there we go. So we can say A has elements AB and B has elements A, B, C. As I said, there's a significant amount of lag. I don't know exactly why. Okay, I'm gonna figure it out. All right, so would this work? In other words, in this case, A minus B is an empty set. Is that true? Is there anything in A but not in B? There's nothing, right? Nothing is in A but not in B. Everything in A is in B. Okay, so we know this particular expression is true. Okay, so now we look at the second part. So the second part is A is a subset of B. It's not the case that A is a subset of B. Okay, and proper subset at that. But that is not even important, because what do we know about A is a subset of B? Is A a subset of B? Yes, it is. So the negation of A is a subset of B is false. True implies false is false. And that's why the statement is false. I cannot say that regardless of A and B, the statement is true. So that's why we have to choose false for question number 6. Question 7 has about the same kind of flavor, except it's a slightly different question, and I think it's easier too. This one is asking, regardless of how I defined set A and set B, if I know that A intersecting with B has exactly the same result as A union with B, does that imply A and B are exactly the same? The answer is yes. Okay? So this one is true. And then we got question 8, about the same kind of question, regardless of how we define A and B. A is an element of B implies that A is a subset of B cannot be true. Okay? So can we construct a case that this is false? That's the question. Okay? What do you think? It is false, okay, because we can find a case where A as a set is a subset of B, but A is not A as a set is an element of B. However, A is also a subset of B. So how do we construct a case like that? Okay, so let me write it down first, and then I'll get to it. So A is an element of B implies it is not the case that A is a subset of B. Okay, so now we can switch to the whiteboard. Okay, so first I have to construct A and B to make sure that A is a set, it is a subset of B, is an element of B. Excuse me, is an element of B. But I also then want to make sure that A is not a subset of B. Well, the easiest one is A is an empty set. What about B? B is a set of an empty set. Okay? Well, okay. It's lagging a little bit, getting there. Mm-hmm. There you go. Yep.
Sorry to interrupt. Just a suggestion. You can use TeamViewer for this kind of stuff.
Can I what?
You can use a software called TeamViewer. You can just basically like show the screen on your iPad on the computer, and it's gonna do right away. Which is like the TeamViewer you can
Oh,
control.
Team Viewer.
Yeah, you can.
Okay. Well, I'll look into that option. Um, so, so it will reduce the lag. Yeah, I'll try to set it up for the next lecture. But in this case, is A subset? I mean, is A an element of B? Yeah. I mean, A is an empty set, and the empty set is an element in B. So that makes the left-hand side of the implication true. What about the right-hand side? The empty set is a subset of every set. Okay? So that means A is, in fact, a subset of B. But if this is true, then the negation of that is false. So I have just constructed a counterexample to show that the statement cannot be true regardless of how I define A and B. Is that okay? All right. So the answer is false in this case. So I submit the quiz, and we'll take a look at the score. So 1 out of 1. This one is not yet graded because it has to be manually graded. The rest, 1 over 1. Okay, so far so good. So I got 7 out of 10, which is the maximum you can get without me grading the one that is open-ended. Do we have any questions about the little quiz or the homework? No? Yep, go ahead.
I still somehow I'm still doing that in number question number 8. I know
Which
what
one?
you did. Number 8.
Number 8?
Yeah, I know what you did, but when I look at it, I'm getting something wrong in the implementation of the way you explained it. I like it.
Okay.
So you said I saw that you proved that A is a subset of B, but because the outside parentheses were negating it, the answer is false. Correct?
Yes. So A is a subset of B is true.
Okay, I got that.
But because of the negation on the outside, this is saying not. So not true is going to be false. So when you look at the entire right-hand side of the implication, it is false.
So how am I reading the whole equation? Maybe that's what I'm doing wrong. When I look at that, I'm trying to prove that.
You are trying to come up with a counterexample to show that I can construct one single counterexample where A is defined like this, B is defined like that, where the expression, this entire expression, is false. If you can create one counterexample, then the answer to the question is going to be false. Because the question said, regardless of how you define A and B, the following is true or false. Okay, so are we okay so far? Okay. So if this is okay, I'm gonna continue and open up the next quiz or the next homework assignment. It's going to be about the same in terms of the format. So I have not assigned it yet, so you guys cannot see it yet. It's about the functions. It's on functions. So this is the function assignment, and I'm going to change the date so that it reflects what it is supposed to be. And we'll set it to 1 week from today. Oh, the 19th is actually correct. Time is not. So we'll make it due at the beginning of the class, which is 4 p.m. and we'll make it available today. Today's the 12th, right? Yep. Okay. And then we'll make it due also at 4 p.m. like that. Save and publish. Question?
It's clarification.
Oh, okay. Thank you. All right. So you have your next homework assignment, which has about the same kind of question. So if I do a quick, preview, you can see it has questions about this. I'm just looking at the notation here. Ah, yeah, it's missing the parentheses. Okay, so when you read the question, just keep in mind that there are some extra parentheses that are missing. The open parentheses are missing.
So it could be three parentheses at the beginning, or each.
Hmm?
It could be three parentheses at the beginning, or each.
Oh, okay. All right, how about this? I'll fix it first and then re-release the quiz, assuming nobody has started yet. Because I know some people just want to jump on these things and go like, I'm going to get started now. Okay, so let me fix that later, and then I'll let you guys know when it's fixed and you guys can get started, okay? Which means I have to remember to do it. And I tend to forget stuff. I'm kind of surprised that the personality thing does not have an assessment on forgetfulness or the ability to remember things. So I'm pretty sure I'm going to score a pretty extreme score on that one too. Yeah. There we go. So here's the row sheet for this class. And just initial your name, next to your name. And that's how we're going to take a row here. Thank you. Right. All right, so moving on, we are pretty much done with Aleph Null. So has anyone read the module on Aleph Null? There are some, a few, okay. Not as many people as I would hope. Okay. So last time we ended up with a discussion of the closed form of g of xy. In other words, if you have a coordinate system, where x is the x coordinate or the horizontal axis, and y is the vertical axis, x and y must be natural numbers. How do we fold that two-dimensional number into a one-dimensional natural number? So last time we already talked about this equation, or how we can define g so that g is bijective. Okay, so we kind of established that already. So the question now, the reverse question is, how do we get back from a single natural number, how do we get back to the xy coordinate? In other words, given that we fill up the 2D space diagonally, and I just throw a number at you, let's say 1001, okay? Where is that 1001 in the two-dimensional space? That becomes the next question. We know it's doable because the function is bijective. Okay, if it's bijective, there has got to be an inverse function. So the rest of this slide, basically talks about how I find the inverse function for function g. Okay. All right. So now we want to kind of look into this and find out. Okay, so how do we reverse the whole thing? So what do you think? How do we reverse it? So we're just going to read it a little bit here. To find the inverse function, we have to find the diagonal line. Because once we find the line itself, it's pretty easy to locate the exact location where that number is. So now we want to find just the line itself. So to find the line itself, we know this. Let's see what w is just x plus y. Okay, remember what what is the significance of x plus y? When you add the x coordinate and the y coordinate of a pixel, okay, of a two-dimensional pixel, and it adds up to be, let's say, W, okay? Why is that significant? It's the base, okay? It is the x-coordinate of the base. And in addition to that, every single pixel along the diagonal line has the property of x plus y equals to W. Okay, so that's why W is significant, okay? But we don't even know what W is, okay? But we know certain things about W because we know, G of W0, which is the bottom, the base of the entire diagonal line, has the smallest natural number mapped to it. Okay, everything else along the diagonal line has higher numbers. Is that okay? So what we're trying to do is to establish constraints. The n is basically the number that is given to us. It's a natural number. It's the 1001 in the example. Okay, so n is 1001. So the first thing I want to do is just to find out which diagonal line contains 1001. Is that okay? So that's why we can establish this inequality. N has to be greater than or equal to W times W plus 1, the whole thing divided by 2, where W itself is x plus y. Is that okay? Let me see if I can explain it kind of graphically using my tablet. And we'll use fine and switch. There we go. Okay. So what we're dealing with here is I'm given a particular number, say 1001. Okay. All right. So that 1001 is corresponding to a particular pixel that has the coordinate of xy. I have no idea what xy is. I just know the natural number that is given to me. So to use the symbol that are already in the notes, we're basically saying n, the unknown n, but not the unknown. The given number n is 1001. The unknown, which are the coordinates are xy, and we don't know what xy is. So now what we want to do is to define W as x plus y. It's just how we want to define it because it's a shorthand. So by doing this, we now say, okay, everything along the diagonal line that xy belong to is going to have x plus y equal to W. But particularly, this thing, all the way to the base of the diagonal line, is going to be W0. Okay, the coordinate of the base of the diagonal line is W0. Is that okay? All right? And we know the value of that thing too, okay, or at least we know how to express it. So the value corresponding to this location is W times W plus 1, and then the whole thing divided by 2. There we go. Is that okay? So this is based on what we talked about in the previous class. So that's one constraint. But with only one constraint, we may or may not be able to find the solution. So at this point, I just expand the whole thing, and I say, okay, so here's the inequality. W times W plus 1 divided by 2 is less than or equal to n. And then just by moving things around a little bit, I end up with W squared plus W minus 2n is less than or equal to 0. Can you guys buy that? In other words, given this inequality up here, can we buy that we can eventually derive it like this? Okay, it's pretty much just algebra. Okay, we are just distributing the division by 2, distributing the W times over here, and then instead of using divided by 2, we use 0.5 times, and then we multiply both sides by 2, so we end up with just W squared, just so that it's easier to look at. All right. So if we kind of ignore that this is an inequality, okay, in other words, if I just turn it into an equality, it becomes a quadratic equation, right? The quadratic equation is just w squared plus w minus 2n equals to 0. It's a quadratic equation. We know what n is. N is the one that is given to us. So we know what n is. N in our case, in the example, is 1001. Okay, so the root of this w is going to be, okay, you just plug it into the solution of a quadratic equation, plus minus, is that b, plus or minus, um, b squared minus 4ac, the whole thing divided by, is it 2a, negative 2a? Okay, 2c, okay. Well, we can look it up. Okay, but this w is going to be one of the roots, but not both of them, because one of these is guaranteed to be negative. So we throw that away. Okay, so we only keep one. We only keep the one that is on the positive side. So that turns out to be the floor. Well, okay, w, if you use this equation, w is not necessarily a natural number. It can be an irrational number. So we have to take the floor of that, because we know x is a natural number, y is a natural number. So when you look at the sum of two natural numbers, w itself has to be a natural number. So that's why we have to take the floor of this. Why are we taking the floor but not the ceiling?
Because below.
Exactly, because it has to do with the less than or equal to inequality. So that means we have to take whatever is possibly the same, but possibly also lower than the actual root. So once we have solved w, the rest is actually pretty easy, because we know that n, which is a given number, is g of xy, and we know we can solve for w now. So now that we know what w is, we can now express y in terms of the given number n and the w that we solved a little bit earlier, and that becomes the y. Once we know the y, x is really easy to solve, because x is w minus y, because the sum of xy is w. So now we have solved for both of those coordinate terms. So both xy are solved. So given all of these derivation, which is explaining more of the rationale of how I come up with these equations, so the cleaned up version is like this. So the cleaned up version is defining w as a function itself. Okay, so w is a function of n, and we are just using the same equation earlier, except this time I'm parameterizing it so that n becomes a parameter. So w of n is the root, is the floor of the root of 8n plus 1, the whole thing minus 1, and then the whole thing divided by 2. Okay? And then we now express x and y also as functions of n, and which is basically just replicating what we had earlier, except we parameterize everything with n. And the final form looks like this. The final form is saying the inverse function of g applied to a given natural number n is a two-tuple. So it is not very often that you see something like this. The result of an inverse function is a two-tuple, even though the function is only taking in a single value. But that's the nature of the problem that we are dealing with. So what about the two-tuple? What is the x and what is the y? X is this whole thing, and then y is this whole thing, and then w is defined up here. All right. So given that my conscientiousness is pretty low, what are you supposed to say? Show it to me, right? Prove it. So how do we prove this? You guys kind of know my way of doing things already. Spreadsheet, very good. So we all have access to apps.losreals.edu, so you might as well use it. So you go to the Google Drive, go to cisp440, the share folder, and then we'll enter the equation. Okay, cisp440 shared, and then we'll make a new document or a new spreadsheet, and I'll call this G function G or aleph no function G. Okay, that might be the best way to name it. Oops. Function G. All right. So we are given n. So this is the actual inverse of that. So let's see, we are given n as 1001. Okay. So the first thing we need to do is to resolve what is Wn. So Wn is going to be an equation. It is the floor of the square root of, I think it's 8 times whatever n is. Was it plus 1? Yep. Divided by, sorry? Oh, is it minus 1 up there? Okay. Yeah, let me just, oh, it's the other tab, so let me cheat. By the way, in the exams of this class, it's open book and open notes. So you can bring anything that is either handwritten or printed prior to the test, and it's okay. Yep. Nope, no electronics. Yep, no electronics. Just open printed or handwritten material. Huh? Does not matter how many pages, nor how many books. It only has to physically fit on your desk. Thank you. Because I really firmly believe that computer science classes really should not be about memorization. If I give you questions that are basically memorization questions, then you'll be spending a lot of juice, brain juice, to do the memorization. But that's not really realistic in the real world. I mean, if you work as a developer or a computer scientist, you probably have a computer that's internet connected to you while you work. So, why would you spend that much time memorizing everything? If you know how to look up something and look it up effectively, that's good enough for me. Okay. All right. So the equation is plus 1, in the square root, minus 1 on the outside, and then we have a division by 2. So we have a minus 1 outside of the root first. Okay, so there's a minus 1 here, and then we need extra parentheses around the whole thing. And then the whole thing divided by 2, like that. And press the enter key. So Wn is now known as 44. So now we can look at what is x of n. And then I'm going to go back to my notes here. So x of n is Wn times Wn plus 3, the whole thing divided by 2. And then minus n. Okay, I can't remember all that stuff. I mean, seriously, I derived this whole thing and I cannot remember it. So I'm going to write it down on a piece of paper or virtually. And by the way, when I said you can use anything that's printed or handwritten prior to the test, that also includes screenshots from the videos. So if you find one particular screenshot that you go like, oh, that's exactly what I want to bring to class, freeze that frame in YouTube, take a screenshot, print it out, and bring it to the exam. That's perfectly okay with me. Okay. Now I did have to say, things that are material that are handwritten or printed prior to the test, because I don't want you guys to write something on a piece of paper, pass on to the next student, and say, but it's on a piece of paper, it's handwritten, so it should be allowed. So it has to be prior to the test. Okay, so let me write down the other one too, which is the y function. Okay, wn plus 1, the whole thing divided by 2. Okay, there we go. All right, so, oh, I keep forgetting it's just another tab here. All right, so the x function is whatever n is minus w times w plus 3, the whole thing divided by 2. Nope, that cannot be the case. Yeah, I think I got it flipped. So it's minus n, not n minus. Okay, this is minus n, like that. Okay, that looks right. And then y of n, I'm just entering what I wrote down on my piece of paper. So y of n is n minus w of n times w of n plus 1, and then the whole thing divided by 2. So I'm basically, according to this calculation, 1001 as a natural number is the location of that in the two-dimensional space is 33 this way and then 11 this way. Well, but I don't trust myself either, okay? So even though I follow my own steps, but there's an easy way to double check it, right? Because I can put it back, I can plug it back into G, then we can figure it out and say, okay, is that coming up with 1001 as the answer?
Yeah, it does.
It does? Thank you. But I'm going to enter it here anyway, just so that people can see it. So we'll go G of x of n, y of n, oops, and then close another paren here. So that would be x plus y times x plus y plus 1, the whole thing divided by 2 plus y, okay? And that turns out to be 1001. So it does work out. And then somebody's going to say, but Tech, I think you just picked 1001 because it just works out. That number is the only thing that works out with given the equations that we have used here. So we'll pick some other number. You guys get to pick what number you want to try. Anything that's a natural number should work. Come on. 6666. Okay. I can buy that. Is that base 7? Oh wait, this is not assembly language. Okay. Yep. It works out. So as it turns out, the number 6666 is located 3 this way and then 111 this way. That's where you will find it. So is that okay so far? I think that's kind of cool, okay? Because you can now fold a two-dimensional space and collapse it into one single dimension. And not only can you do that, it is a bijective function. So given any natural number, you can reverse it back to the xy coordinates. Yep.
Everything in the universe is countable.
No, because real numbers are not countable. Real numbers, sorry?
I mean, you see the cardinality of, we can have the cardinality of n. So when you fold two dimension into one,
Mm-hmm.
even if you don't know the number, it's countable.
It is countable, correct. But we are only dealing with, remember the set of natural numbers is countable, but the set of real numbers is not countable. There's no way that I can come up with a bijective function between the set of all natural numbers and the set of all real numbers.
Okay, so what if you take a three-dimension space
Yes.
and then 6 and 7.
Yep. As long as each axis only has natural numbers as for measurement. Yes.
Okay, then that's fine.
So that is a very important condition. Now you can extend the requirement of natural number to integers because we know how to fold integers into natural numbers already, right? So that means the axes can be in integers as well because we already know how to fold integers into natural numbers, and then we know now how to fold multiple dimensions of natural numbers into a single dimension natural number. It's kind of cool. I mean, conceptually, it is kind of cool. Yep. All right. So we are pretty much done with Aleph Null. Are there any questions? Okay. So when you think about questions, think about questions in 3 different levels. Okay. The pine needle level. The pine needle level basically has to do with the square root, the floor, the actual definition of the functions, stuff like that. At the tree level is, oh, what is G again? Is it a function? If it is a function, what is the domain and what is the codomain? Okay, is it bijective? Is it injective? Is it surjective? So that is taking a step back and look at it at the tree level. And then we take another step back and ask, at the forest level, why is this important? How does it relate to the discussion of set theory? I mean, why is it important? Exactly, because it's a bijective function and it maps to natural numbers. This is how we define infinitely countable sets, which also they're also known to have a cardinality of. You're looking at the screen right now. The cardinality of the set of natural numbers is Aleph Null. That is the definition of Aleph Null. Okay, so now you can see why we kind of have to take a slight detour to talk about functions first before we get back to talk about Aleph Null, because we need that concept of a bijective function to establish whether a particular set has a cardinality of Aleph Null. Are we okay so far with this? Okay, so we are going to take a small, short break from functions, and then we'll start to talk about relations. So in discrete math, relation is basically how elements in a set relate to each other. To be more exact, it is asking, are 2 particular elements of a set related in a particular way? So what we'll do is we'll look at a relation, and we'll start with the description of what it is. So a relation is whether 2 elements of a set are related or not, but it's position sensitive. In other words, you can say A relates to B, but B does not relate to A. Okay, so those 2 relationships are distinct. So you can have the presence of one, but the absence of the other one. Okay, so in real life, we have a lot of relations. Okay, parenthood is a relation. Okay, is A parent of B? Okay, that's a relation. Seating arrangement in class can be a relation. Is A sitting in front of B? Okay, that's a relation. In computer science, in programming, we have a lot of relations. Less than is a relation. Is A less than B? That's a relation. Are we okay so far? With what a relation is? Okay. So when we talk about relation, we talk about the relation whether it is a relation that is defined over a particular set. So now we do not have 2 different sets, potentially 2 different sets. We only have one single set X, and the relation applies to elements of X and element of X. So we do not have a domain and a codomain. We simply have one single set that the relation is defined over. Okay? But we are looking at relation as a set again. So you can see this notation. X cross X is a Cartesian product. Okay? and relation is a subset of, and this one really should be a subset of and not a proper subset of. So let me fix that because I really hate these incorrect notations on my because of my error. Okay, so you can now see how I fix my notes. Okay. Yeah. There we go. And what is the module number? Say it again.
0312.
Oh, okay, 312. Okay. Okay, so it's a subset EQ. And then we republish everything here. I wrote a small script to kind of simplify the whole thing. And now we can go back here, refresh. Ta-da! See how easy it is to fix my notes. Once you know LaTeX, it's really easy. LaTeX, L-A. Okay, so LaTeX. Okay, for those of you who are interested, the typesetting software that I use looks like latex, but it's actually pronounced LaTeX, because LA is actually in the English alphabet, but it's tau epsilon chi in the Greek alphabet. So that's why it's not pronounced as latex. It is actually LaTeX. I don't speak Greek, so I can be off. Okay, so R has to be a subset, not proper subset. It's just a subset of the Cartesian product between x and x. Okay, so without knowing what is a relation is, just looking at a Cartesian product, what is the basic format of an element inside a Cartesian product? It's a tuple. Okay, each element is a two tuple. So within a two tuple, we have two things, and the presence of a two tuple basically says the first item relates to the second item, and both items must be in the set where the relation is defined over. Is that okay? So let's go ahead and create a few examples. And let's see, switch back to here. So we can say, so you can define R to be whatever you want. So I'm going to define R to be, I don't know, 1, 2, 3. So this is really, really arbitrary. I'm just giving you an example of, a relation. Doesn't mean that it has to be useful or meaningful in any way. And then I define, oops, I take it back. Wrong notation, this is x. Because R is defined over x. So R is defined as, okay, let's say 1, 2, and 2, 3. Okay. So this particular R, which is a set of two tuples, is a subset of x Cartesian product with x. So it is a relation. 1 relates to 2 for whatever reason, okay, I don't know exactly why. 2 relates to 3, okay, but there are no other further relations. In other words, 3 does not relate to 2. It is not bidirectional. And 2 does not relate to 1 because there's the absence of 2, 1 as a two tuple. So is that okay? Now, I can also have relations where 1 relates to 1, but it's absent here. But it is perfectly okay for a relation to have a particular element relating to itself. So in C and C++ programming, equality is kind of like that. So for any particular value, that value equals to itself. So is that okay? As an example of a relation. Any questions about? Yeah. A relates to 2. Mm-hmm. That's the convention of how you read a relation as a 2 tuple. See, I'm traditional. I don't know why they say I'm only at 1 percentile. Okay, so are we good? All right, so there are other ways to specify these relations as well, because you can also write in shorthand AR2 and 2R3. So those two are true expressions. So 1R2 is true, 2R3 is true. What about 1R1? False. Okay, that relation does not exist. So 1R1 is going to be false. So to be more complete, we'll just say that these are true. And then I can give you some examples of 1R1 equals to 3R2 equals to 2R1 equals to false. But the list is not exclusive. It's not inclusive. It's not exhaustive. Okay, that's the word. In other words, there are other ones that are false as well. 3R3 is false. So are we okay so far with the notations? Just the notations. Yep.
101 is only false because the 2 tuple 1 comma 1 doesn't exist in R.
That is correct. Because 1, 1 as a 2 tuple does not exist in R, that relation 1R1 is false. Okay? Yep.
Do we have relations between empty sets?
Between empty set. So you're defining X to be an empty set, right? Okay, yes you can. It's trivial, but you can. Okay, so let's go ahead and explore that. So what he's talking about is X is an empty set to begin with. So the only relation you can define over an empty set is the empty set Cartesian product with empty set, which is an empty set itself. So R has to be a subset of an empty set. As a result, R has to be an empty set. But it is a relation, okay? It's just a trivial relation. It's a relation that has no elements in it. Okay? So that's a very good, interesting observation, because when we start to talk about properties of relations, we can actually talk about certain properties of the empty relation, which is in the empty set. Okay? So are we okay with all of this so far? You know, just notations. Okay. All right. So now we'll start to, okay, there's a concrete example here. So normally, you know, we have the less than relation of integers. So that's why, you know, 1 is less than 2 is true. So 1 relates to 2 through less than is true. And that's because 1, 2 as a 2 tuple is an element of the less than relation. Okay, so both of these are basically saying the same thing. And then we got some random examples. You know, we already talked about this. So now we talk about properties of relations. And yes, we are going back to the dreaded quantifiers that we have already talked about when we talk about set theory. So the first one is called reflexive or reflexivity of relations. A relation R over a set X is said to be reflexive if and only if the following condition is true. If you say that for every single element in X, E E as a two tuple is also an element of R, then if this is true, then R is reflexive. Is that okay? So if I have, so let's say X has the elements 1, 2, and 3. Okay? What is the minimum R that can make R reflexive? Sorry? Not any one, because it has to be for all. So that means 1, 1 as a two tuple, 2, 2 as a two tuple, and then 3, 3 as a two tuple. Those three tuples must be in R in order for R to be called reflexive. If you miss one of those three, it is not reflexive anymore. If you have additional ones, it's fine, because it doesn't say that it cannot contain additional relation, it contain additional tuples. It just says that 1, 1, 2, 2, 3, 3, those three, they have to be in R in order for R to be reflexive. Are we okay with the definition of being reflexive? So each element has to relate to itself. Question? Question? Yep? No? Okay.
I was gotta say,
Okay.
what you just answered with, it means that every element relates to itself.
Yeah, in order for the relation to be called reflexive, every element of the set that the relation is defined over has to relate to itself. So in arithmetic, in computer programming, less than or equal to is reflexive, because every value is less than or equal to itself. Equality is reflexive, because every value equals to itself. Inequality, not equal to, is not reflexive. Okay? Less than is not reflexive. Greater than is not reflexive. So is that okay? Those are kind of examples of relations when it comes to whether they're reflexive or not. So symmetry or symmetric is defined like this. A relation R defined over a set X is symmetric if and only if the following is true. If you consider any two elements of X, which is the set that the relation is defined over, EF as a two tuple in R, it can be in R if and only if FE is also in R. Now, this one is a very tricky definition. Okay? So I'll give you some examples. I'll give you an example that is really obvious first, and then I'll give you one that is not so obvious. And this time I'm going to use just a text editor, because it's just faster to write these things using a text editor. All right, so we'll go to mousepad. And I still show the definition up here. So I will say X is just 1, 2, 3, or ABC. Okay, so it will have ABC here. And then R is AA, BB, and CC. Okay, so the first thing we notice is R is reflexive, because for every single element in X, it relates to itself. Okay, so that's not a problem. Is it symmetric? AA is in R. Oh, AA is also in R. No problem. BB, CC, they're the same. Oh, what about AB? Well, AB does not exist in R, but you know what? BA does not exist in R either. So we are good. Because this is if and only if. When you're dealing with if and only if, when both sides are false, the if and only if itself is true. So that means the absence of AB and the absence of BA is actually perfectly okay. All right? So this example is reflexive. Okay, so we'll go ahead and say this is actually, it's reflexive and symmetric. Okay, so I'll give you another example. Same X, and this is a relation defined over X. This time we're dealing with an empty relation. R is an empty set. So is an empty relation reflexive? Okay, so we'll first answer the reflexive question. It is not reflexive because X actually has elements A, B, and C, but A does not relate to A because there's no relation whatsoever defined here. B does not relate to B, C does not even relate to C. It is not reflexive. But is it symmetric? It is symmetric, okay? Because if you consider every single way you compare elements in X, okay? Okay, let's say E and F are both A, right? AA is not an element of R. That's fine, because AA is not an element of R. So we have both sides of the if and only if being false. The if and only if itself is true, okay? What about A and B? What if I pick E to be A and F to be B? Well, AB is an element of R is false. BA is an element of R is false. False if and only if false is true. Okay, so in fact, if you pick any two elements of X, you will find that this if and only if continues to be true. So the empty relation is actually symmetric. So this is not reflexive, but symmetric. Symmetric. There we go. Okay, so let's take a look at this one. A, B, B, A. Definitely not symmetric. Okay, not reflexive, but is it symmetric? It is symmetric. Oh, but what about AC and CA? Well, they don't have to be here, okay? Because if AB is here, A is here, it's good enough. Okay? So this one is not reflexive, but it is still symmetric. So now we'll give you an example that is reflexive but not symmetric. So it's AA, BB, and CC. And then we just have AB and BC. This is reflexive. Reflexive. It is reflexive because AA, BB, CC are in R. Okay? That's all it takes to qualify as being reflexive. In other words, a relation can be reflexive and something else. That's perfectly okay. But it is not symmetric because AB is here, but where's BA? Not here. So when you look at this expression, AB is in R, but BA is not in R. So we have true if and only if false. That if and only if is false. Okay, so the if and only if can be true if and only when both sides are the same. They can both be true, they can both be false, but not one is true, the other one is false. Okay. I'm just looking at the time. We got 2 minutes. So the next one is transitive. So once again, transitive relies on a tricky operator. This one relies on implication. But this time we have to pick any 3 elements out of the set X. It says here, for all the ways you can pick elements E, F, G as elements of X, I need the following implication to be true. What implication are we talking about? If EF is in R and FG is in R, then EG has to be in R. Okay, if this conditional state, if this implication is true for any 3 elements E, F, G that you can find in X, then the relation is called transitive. Okay? So we'll take a look at a transitive relation. In fact, we'll look at all the old relations that we have already explored and say, is this transitive? Is this one transitive? We only got AA, BB, CC. Is it transitive? It is transitive. Okay? Okay. So this one is in fact transitive. Why is it transitive? It's because of the implication. This one is transitive as well. The empty relation is actually transitive, because if you look at this whole thing, if for an empty relation, can you find me two elements EF such that EF as a two tuple is in R? No. Can you find me two elements FG so that FG is in R? No. No, false, and false is false. Okay? Can you find me an EG in R based on the constraints of the first part? No. So we end up with false implies false. But what is the value of the implication when we say false implies false? The implication is true. So for every way to find three elements in X, this implication turns out to be true when the relation is empty. There's nothing in the relation itself. So this is really not intuitive, right? Okay, so what about this one here? Is this one transitive? It is not transitive. Let me see. Yeah. It is not transitive. Okay, I can tell you why it's not transitive. Because AB is in R, BA is in R, right? So now we have true and true. Is AA in R? Nope. So we have now true implies false, so the implication itself is false. So that's why, when the relation is ABBA, it is not transitive. What about the last one? The last one has AB, has BC. Okay, so this is important. So basically, what you're really looking for is the presence of what I call a bridge element. Okay, so this part is not traditional. That's why I'm in the 1 percentile. Okay, because I've never seen any documentation saying mentioning the word of a bridge element. B is a bridge element. Okay, it's bridging ARB and BRC. Okay, so AB is in R, BC is in R, AC is not in R. So once again, we have true and true being true, and then we have false on the other side of the implication. We have true implies false, which is false. So yeah, go ahead.
I was going to go back to the other one where you were saying A, B, and BA.
Yeah.
So E and G can be the same letter?
Yeah, they can be. Yep. Because this is saying for any three elements. Okay, pick three elements, but they can be the same, they can be different. Two can be the same, the other one being different. It doesn't matter. For every way to pick three things out of the set, the following has to be true.
Well, it's the first and last.
Yep.
I get that this won't be transitive, but what about a set that you had like AA in it?
A set that only has AA in it,
Or like won't be
then it is transitive. Yep. So it's transitive, not reflexive, and symmetric. All right. So we'll continue this discussion on next Monday, but your job is to read up to this point and a little bit ahead of me. So try to finish the entire module on relation before Monday when we talk about it.